Okay, hello everybody. So I'm going to try to record this again today. The reason I didn't post the other ones is the audio is just really bad. But today, I'm going to try it one more time and just see. See, like right now I'm speaking. If I speak loud enough, it'll sort of pick it up, but it really doesn't. Okay, so I updated the problem list. And instead of the schedule used to be that we were going to move on to section 4, but now the schedule says that we're waiting until I guess the 29th to read section 4. So for Monday, just we're going to slow down and still do basically the same problems. I added one more problem on derivatives, aka tangent space and normal space calculations. And the reason I do that is because, first, that is sort of going to be useful in so many different classes, not just math, but also other classes, and also just other math classes too. The derivative is the most central thing in calculus, and calculus appears everywhere. And the point of calculus is to take the derivative so that we can just do linear algebra, because linear algebra is what we're good at. And this is just like the theme of all of mathematics. This just shows up again and again. Basically, this class is like the one time where we actually try to work with the original nonlinear equations. And even then, we basically can't solve it in general. Sometimes we can solve it if we use computational techniques that we'll learn in this class. And this is only for polynomial equations. Then if you try to do more complicated equations, it gets even harder. So we're going to pause and think about the derivative. And so on the Canvas homepage, as always, is everything you need. The updated problem list is there. And so I have it, I downloaded it. And so these are the problems that you had already seen. Here we're parametrizing a linear variety in problem 9. Then this one is where we learn about the derivative. And specifically, what does the derivative mean geometrically, right? Because this is algebraic geometry class. And then this question is just getting you used to the idea of maps, because everything in algebraic geometry is either a parametrization map, like section 3, or a vanishing set map, like the entire rest of the book. And so, yeah, and by the way, the reason the book will basically be dealing with pre-images of maps rather than images, aka implicit representations rather than parametrizations, is because most algebraic varieties do not have parametrizations, at least by rational functions. Okay. Now, I assume that everybody knows that I put up a solution video for problem 10. Yes? Okay. So good. When you get stuck on that solution video, you can right-click, and it'll bring up an option of copy video URL at current time. So if you get stuck on something that you don't know what I'm doing, just shoot me an email with the exact moment in the video, and I can usually answer the question pretty well. Okay. All right. Then what I'd like to do is talk about one of the new questions, problem 13. Okay. So no. Actually, before I look at problem 13, can everybody take out a blank sheet of paper, please? So right now, let's just see how we do on problem 10. So I'm not going to give you enough time to completely solve the problem, but I'm going to give you 5 minutes, and actually I'll have you turn this in just so I can have a sort of a check-in of how we're doing, so I know if we should slow down more or if we should speed up more. So I'm going to set, this is how I study. I set a timer, and then I have silence while I just think and write. So 5 minutes, maybe, oh, no, 5 minutes. Okay, so problem 10 is right here. Just see how much you can remember and solve of it. I'll do the same. Okay, so, okay, let's see. Yeah, still take a moment. I'm going to attempt to take a picture of my screen. Can I do that? Image, camera. Oops. Well, that'll have to do. Okay, so just briefly, I'll describe what I did. In order to show you something new today in class, I used a different parametrization than the one I did in the video. Namely, I used not actually the spherical coordinates you see in physics usually, but some other spherical coordinates that are just as good. In fact, I think these are actually longitude and latitude. But either way, so I took like some cosines and sines, and I created a map, F. So this map, F, sent theta 1, theta 2 to a point on the unit sphere. And then I had to figure out, how did I get this, because the problem wanted me to do this specific point, 1/2 root 2 over 2. And so I had to think about my parametrization and then think about the unit circle, just the unit circle, not the unit sphere, to get the right angles. And I think it's these two angles that would give me the correct point. Then I took the derivative. So here's my map F, and I took the derivative with respect to theta 1 and put it in this first column. And I took the derivative with respect to theta 2 and put it in that second column. Okay, and then I knew that if I just plug in this theta, I'm going to be at the correct point. So if I plug in that theta at here, my derivative has a basis of the tangent space built into it. Okay. Let me just pause for a moment. So I guess I got that far. I got a basis of the tangent space. Right away, because we're in R3, I can use the cross product and be done. But I just really don't like the cross product. So, because it only works in R3. It's sort of just an accident that the Lie algebra of SO3 is three-dimensional. That's why we get curl, and that's why we get cross product. The Lie algebra of SO4 is six-dimensional. So it doesn't work anymore in four-dimensional space and higher. Wait, is it six-dimensional? So I have four. I need 1, 2, 3, 4, 5, 6. Yes, it's six-dimensional. Okay, we will get there eventually when we study algebraic groups, which are algebraic varieties that are also groups. Okay, but that's later. Okay, first, any questions on what I did? Yes, Kinry.
Can you just walk us through the parametrization?
Sure. This is a useful one. In particular, because to me, it's easier to see how it extends to n-dimensional spheres. So the sphere, the two-dimensional sphere, has inside of it a unit circle, right? So first, I just parametrize that unit circle. So here's my unit circle. Somewhere is the x1 direction, and maybe here's theta. So now I get a point right there. But that point right there is actually, I'm just going to give it a name. I'm going to call it V. and it's cos of theta 1, sine of theta 1, comma 0. Do we agree? By the way, one of the most useful things I can tell you is do not write out cos of theta 1 every time. You can just write c sub 1. And you know what it means, and you know that c1 squared plus s1 squared is equal to 1, and you're good. You can do all the calculations. You just don't have to write so much. So, is everyone okay with this being that point? I clearly don't have the whole sphere yet. Okay, good. So now I'll go purple, and I slice with a plane along the vector v, spanned by v and the E3 axis up to the North Pole. So the purple plane equals span of, can you even read this? Oh yeah, you can. Okay. Span of v and E3, which is, secretly just the vector 0, 0, 1. Okay? Now, in that two-dimensional plane, I just rotate again. And that's it. And so what do? I just take sort of an arbitrary point up here on this circle. Now this will be theta 2, theta 1, theta 2. And now I'm getting, well, let me get a darker color, purple. This point, which is now like an arbitrary point on the sphere. First I rotate around the unit circle, and then I rotate up or down. And so this point here will be cos of theta 2 times v, the entire three-dimensional vector v, plus the sine of theta 2 times E3. Okay, because that's basically what you're doing with this parametrization, is you had cos of E1, sine of E2, and that was the E1, E2 plane. So this is sort of a nice, you see how useful it is to give things a name and then calculate with them, remembering what they are, that secretly V is a vector. And I just expand it out and I get the parametrization that I wrote, and I called it F. Does everyone see that? So like C2 times V is a scalar times a vector. And so what is it? It's C2, C1, C2, S1, C2 times 0, plus S2 times 0, 0, 1 is just going to be S2. I just eliminate. Okay, and then together we get a parametrization like that. Okay. And now we realize that we have a point on the sphere which is a sub-object of the three-dimensional sphere. The three-dimensional sphere, which is related to the group SU2 from particle physics. Very, very, very closely related, and spinors. But now all we need to do is just, let's parameterize the three-sphere. So let's call this thing, no. Let's call W, we're going to define, I like define to be equal to, C2, C1, C2, S1, S2, 0. Okay, so now we're sitting inside of the three-dimensional sphere on sort of its equatorial three-dimensional cross-section. Just repeat. Now we just go cos of W, cos theta 3 of W, plus sine theta 3 of E4. And we get the three-dimensional sphere. So a parametrization of, so let's say a map from theta 1, theta 2, theta 3. Well, that's not bad 3. It gets sent to what? Well, it gets sent to cosine of theta 3 W plus sine of theta 3 E4. E4 is 0, 0, 0, 1. Okay, so now we've parametrization of S3, subset of R4, related to the groups SL2, whose maximal compact subgroup is SU2, and you can disregard this if you're uninterested. Okay.
Actually seeing the pattern now when I write it out.
It is nice, yeah. So, but the wonderful thing about parametrizations is that when you have them, you can generate as many points on the object as you like. You really have a lot of control of this geometric object. So, in particular, like for example, in my own research, once we parametrized this geometric object, we could immediately prove wonderful geometric facts about it just by doing a calculation. And yeah, and so the biggest part of like one of my research projects was getting the parametrization of this geometrical object. Yeah. So this is not easy, but it's definitely worth your effort. Okay. Now, back to the point of this. Once I have this parametrization, can we see it up there? I take the derivative with respect to the first parameter, and it gives me one basis vector of the tangent space. And I get the derivative with respect to the second factor, it gives me one basis vector of the tangent space. Okay. Does this intuitively make sense to everybody, or no? Okay. I want to give one more picture of intuition. So we're done with the formulas, but now this is now sort of our thinking about this. What I have here is I'm mapping a two-dimensional plane into three-dimensional space. Agree? In a nonlinear way. Cosine and sine are nonlinear. And so what I have is I'm just mapping like, here's theta 1, theta 2. And it gets mapped over by f to some spot on the sphere in three-dimensional space. Let's say f of theta. And then what you think of is, imagine running along this blue line with velocity this blue vector. Well, then that blue line goes somewhere non-linearly on the sphere with velocity maybe this blue vector. Okay, and that is that's why the derivative of theta with respect to theta 1 gives you a tangent vector, one of the bases of the tangent space. Okay, because the image of the map is our object. We can do the same thing but with a different color. If we imagine this green line and we travel with velocity this vector, then that will go to some sort of, who knows, maybe it goes this way. With velocity this green vector. Okay, and so together we start to get a plane when we start sending all the points by the derivative. That goes where? I guess here. And over here, these are not squares anymore. They're most likely parallelograms. And when we're integrating over the sphere, we need to take into account the shrinking or the growth of those parallelograms. Right, so this little unit square becomes some bigger volume parallelogram, and this is the factor the change of variables factor in the integral. Okay, good. Now, let me just pause for a moment. We're supposed to be doing algebraic geometry. Well, the most interesting parts of algebraic geometry are its singularities. how do you find them? Singularities is where this stops working. Okay? And so that's why we're interested in this, I guess, for this class. So, I guess I'll say foreshadowing. Foreshadowing the singular points of a variety will be where the derivative breaks down. And for now, I won't say what breaks down means. Okay, I will. It drops rank. Okay, derivative is a matrix, maybe it's rectangular matrix. Here, it was a 3x2 matrix on the board. And typically, it's rank 2. A 3x2 rank matrix usually has rank 2. But sometimes the rank will drop. Could be rank 1. Could be rank 0. And at those points, those are going to be singular points. Okay. Yeah. By the way, like same thing like black holes. They call them singularities because that's where space-time ceases to be a smooth four-dimensional manifold. And where the derivative breaks down is what we call singularity. Same thing. This is what you mean in, for example, the equations that tell you the curvature of space-time as a four-dimensional object. Of course, space-time is probably not an algebraic variety. Maybe I don't know. Nobody knows what it is, but definitely what they mean when they say singularity is the derivative stops working, and so it's not flat, and space gets weirder. Yeah. Okay, good. Now I would like to open it up to you. You have had 5 minutes sort of alone thinking. And then now you've seen, I don't know, like 10 minutes of me talking, 10 minutes of my thinking. So, questions? What about the way you did it? Probably with a different map, but how far did you get? What parts are still confusing?
Oh, I feel like you just gave me a good intuition for why the derivative of the image map, or the map of that's an image of a shape is a tangent. Is there a similar intuition for why the derivative of the pre-image map is the normal?
Okay, excellent question. Yes.
Okay.
Yes, and but it is very different because there's always two sides of the coin: parametrization or implicit. Parametrization is the image or pre-image, and so yeah, maybe we talk about that next. Does that seem like a good nod your head if you think that's a good thing to talk about? Okay. Yeah. Okay. Yes. So, what about pre-image? So should we just take the sphere again and let's try to do the image? So, what's that?
Why not?
Yeah, why not? So I think I did part of this in the video, but maybe I didn't give the intuition. So the sphere is also equal to the pre-image of 0 under the map x1, x2, x3 gets sent to x2 squared plus x3 squared plus 1. To discover this equation is actually a problem we can solve using our book, which is pretty great. And we'll see this in the second part of the class, once we get out of chapter 1, is that given a parametrization, the computer will spit out this equation, which is really nice. Yeah, okay. So, what do? Okay, well, let's take the derivative. Let's call this f. df at x should be, okay, well now the output is one-dimensional, so typically we write it as a 1 by 3 matrix. And I just take the partials. And there's the derivative. Okay. So it's a linear map from R3 to R1, because our map was a nonlinear map from R3 to R1. The derivative is a linear map. Namely, it sends like the point v1, v2, v3 to this point in the real numbers given by matrix multiplication. Okay, so now let's try to do the picture. So, so we have our sphere. And let's say we have our point on the sphere, P. Okay, there's the point P. And now, what are the tangent vectors here? So we know that the tangent space should look like this. We can compute it by the parametrization explicitly and find this exact plane. But let's think of now the tangent vectors. Let's say this pink one, or this green one, all of them. What do they satisfy? Well, they have the property that to linear approximation, they stay on the sphere. Okay? So if I went in some tangent vector that was like coming out of the surface at some angle, that's a direction I could move. I could just move away from the sphere, like immediately off the sphere and out into space. For example, I could move radially outward from the origin. Now, that's not a tangent vector. Why? Because the function f, the value of our function f, increases. But some motions are special. I move, and I'm basically still, the function's value is very much almost the same. Maybe it moves a little bit. If you move in the tangent space, you're going to be off the variety a little bit. You're going to be off the sphere a little bit. But to linear approximation, you're not. So that's why, I guess that's one intuition for tangent vectors give zero change in the value of f. To linear approximation. Okay. Question? Yeah.
I'm like thinking in my head of like putting a ball on like a piece of paper, and that seems weird to me, that like the point of, you know what I mean, like isn't the point of the tangent that it is only touching at that one place, so it's not equal but it's close enough?
Yeah, so you're right. Like
So
if you move away,
yeah,
you're going to be definitely off the ball.
but if you
off the
stay
sphere.
at that point P, any tangent vector that comes off that point is going to be pretty much the same.
Well, to linear approximation, the function f doesn't change its value, and so that's why it's a tangent vector. As opposed to like if you move directly towards the interior of the ball, or if you move directly away from the center of the ball, then the function's value will change rapidly. In fact, one way you can think of this derivative here is as a gradient vector. And in calculus, you learn that the gradient is the direction of steepest ascent. The function value changes most rapidly in the gradient. And so, I mean, that's almost another way to say it, is that let's take this, let's call this an orange vector. And this orange vector is the normal vector. And it's 90 degrees to the plane. So it has 90-degree angle with respect to the green and the pink vectors. And that 90-degree angle, the dot product is 0, is what we mean by a tangent vector should have the dot product with this gradient be 0.
Okay.
So maybe that's sort of another way to think about it. It sort of all comes from the fact that for any map, f of x plus a little change, is approximately equal to f of x plus the derivative of f at x evaluated at v, plus the second differential of f at x evaluated at v comma v, plus dot 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 dot, and this maybe needs to divide by 2 or something.
Whatever.
Yeah. But really, we almost never use this. We will maybe. Actually, this is really interesting, so I don't want to discount the Hessian or the second order differential. And this works for any map f from Rn to Rm. So for a map f, we have Taylor approximation. And so, tangent vectors, so in this sort of setup, tangent vectors v are those with dfx of v equal 0. So they're all the vectors v which are in the kernel of this matrix. And in this case, we have a 1x3 matrix. Its kernel is 2-dimensional, and that is exactly the 2-dimensional tangent space. Okay. So because if dfx is 0, then f of x plus v is approximately f of x plus 0. No change. The function value stays exactly how it was to linear approximation. Okay? So, that one's, to me, this is always a little bit less intuitive, why I get the tangent space this way. But this is my best answer. Mitchell, does that satisfy you?
Yeah. It's better now. I can think about it more too. Maybe you'll ask more.
Yeah.
Wait, Mitchell, wasn't your question about the normal space?
Yeah.
Am I remembering?
Oh, really? Oh, shoot.
Oh, yeah, it was, I guess. But I guess that's like intimately related to the tangent space.
Yeah, it's okay. So yeah, let me address that. Let me think. What do I say? I mean, basically, if you know the tangent space, you know the normal space. If you know the normal space, you know the tangent space. Provided you can solve linear equations, right? Namely, the linear equations something times something equals 0, where we have a vector times a matrix times a vector equals 0. Like here, like these linear equations give the tangent space as a solution, whereas the row space of this gives the normal space. Just like the column space of the derivative of parametrization gives the tangent space, the row space of the derivative of a implicit representation gives the normal space. So it's, like, everything is just flipped. Yeah. So, I mean, why don't I just write that down? So, let f be a parametrization of x, some algebraic variety or manifold. Then the column space of df at x is equal to the tangent space at the point x. And the kernel of df at x is equal to the normal space and this should be f of x. Okay, and then the flip side of the coin is let G be an implicit representation of X. So X is the preimage. Then the row space of GG at X is equal to the tangent space to X at X. And the left, and this is right? Oh, the left kernel should be up there. Well, okay, it just depends on what you call the kernel. You could say the kernel of A transpose, the kernel of dfx transpose, but let's say the kernel of dg of x is equal to the, whoops, I switched this. Okay, so this is why it's useful to write this down. Make sure we get it correct. Okay, so here we have x is preimage of 0, and here x is the image of f. Let's stare at that for a moment. You see how these two fundamental ways of representing a object just sort of flip things.
I'm forgetting what the kernel is.
Yeah, so let's say maybe the right null space. Is that a better word? Right, I kind of like that better, so let's use that. Because then I can say left null space up here. Left null space. And this is the, now instead of kernel, I'll say right null space.
What do you mean when you say left and right?
So then let's write that down too. One of the hardest things about math is just there's so many different words for the same calculation, for the same formula. Luckily, there's always one formula that works, but then there's different notation for that formula. But at least the concept, derivative, is absolutely fundamental. It's everywhere. So you can call it what you like, but let's say, recall the right null space of a matrix, let's say A, is the set, and it'll in fact be a subspace of all vectors V such that AV equals 0. The left null space of a matrix A is the set of all vectors V such that V transpose A equals 0. Okay. A good example is when we had that 1, 0, minus, was it minus root 2? 0, 1 minus root 2. Then all the vectors with this was the, gave the tangent space. No, gave the normal space. Why the normal space? Because this was a parametrization of circle. Okay. Okay. let's do, okay. How many of you finished problem 10 already?
Like in the time that we have.
Yeah, in the 5 minutes. Okay, let's do problem, let's try problem 13. This is new. So let's take 5 minutes and let's try it, and then I'll discuss it.
Do you want us to write it on our quiz paper, or?
Yeah, can you draw, like, on the quiz paper, draw a line so I can see the separation? Yeah, across the horizontal. And then let's work on problem 13. I'll look at it too. another minute and don't look at my board. Or at least don't write anything down on a sheet of paper. Okay. Finish up the last thing you're writing. Okay. Okay, and I'm not going to actually grade these quizzes because, again, I actually view this quiz as a check-in for you on how you're doing with, I guess today it's just derivatives, but also as a check-in for me. So it's a formative assessment, not a summative assessment. In other words, at the midterm, I would like you to be able to solve all the problems we did so far. But right now, I'm just trying to help you get there to, say, the midterm. And with the final, I'd like you to be able to solve all of them by yourself, and I'll grade you on it. But right now, I'm just trying to help you get there. So, can you just pass up your thing, the quiz? Thanks. I'll just see where we're at. I think you already sort of know where you're at, having just done the quiz. And so I guess I'll start by discussing what I did. So I didn't finish the whole thing, but here's the parametrization. And so for the parametrization, the image of the derivative is the tangent space. That's sort of the easier one intuitively for me. And so the two-dimensional subspace of vectors orthogonal to this vector is the normal space. In my picture of this curve, I'm at a point on this curve, and the normal space is a plane. And the tangent space is the tangent line to that curve. Yeah, I think you can see. Now, what I did is I took the given map, which was a map from R3 to R2, and its pre-image is we'd expect it to be a curve. It is in fact a curve. And so the derivative is then I wrote down a 2x3 matrix. It is a linear map from R3 to R2, whereas our original one was a nonlinear map. And now the row space is the normal space. Good, because there's two rows, and they're independent, so we get that plane in the picture. If here's the point 2, 4, 8, then there's that plane. And then all the vectors orthogonal to those two are the tangent space, which, good, it's one vector, or every multiple of that vector. And you can even just sort of by inspection look at this matrix and see that if you put a 1 in the first slot, then you're going to need a 4 there and a 12 there to get zeros with the dot product. So, yeah, any questions on this one?
The step I missed was just turning the map you gave us into the parametrization. And you just do that by solving the equations, right?
Yeah, good question.
And eliminating variables.
In general, given this map, we will not learn an algorithm in our book that will spit out this.
Okay.
So in general, this is sometimes impossible. So I'll just point that out right away. Not clear how to do that in general. In this case, usually if we think about it for a while, we could get it. And this is such a great example that it's worth just memorizing, actually. Yeah, especially when we go to projective space with this thing, something weird will happen, and it's the first example of that weirdness is this curve. So, okay. Let's just stare at this. Any other questions? Me?
I think I created the 5 different maps to the image of V.
So a different one rather than this one?
No, actually the image, yeah.
This one?
Yeah, so I map the point x, y, and then x, y, because z is equal to x, y based on the questions that we have. So is that okay if I leave like z equal to x, y there?
Oh, I see. Okay. So first, to make sure we're on the same page, see how the z coordinate is equal to x times y?
Yeah.
So that is sort of interesting. It also shows we could have defined this curve with different equations. Not just these ones, but we could have said z minus xy. That would have been accurate. So when defining a map from R3 to R2, we have to first decide on names of R3. So just what are the names for the coordinates on R3? And so, for example, we could do x1, x2, x3. Or we could say x, y, z. But if we do like this, even though in this example it seems like it is correct, we have to, I guess for me, like, these are just the names. And so if we do this, it's going to get really confusing. Because now I have to remember that my name is actually two symbols, or 2 letters in the alphabet rather than just one. So, yeah, does that answer your question? Yeah, so this is really good to get straight, is like, how do we write down maps? Because then we have to be able to tell a computer what map we're talking about. And there's where it'll actually really break. So you could probably figure out a way to do this and get the right answer, I bet. But the computer would have much harder time. Okay, good question. All right, do we feel, raise your hand a little bit if you're feeling much better about derivatives. Okay, good. Okay, because last class do you have another question?
Yeah. So the point, like the image of these in R2 should always be 0.
Well, so when I'm just defining a map, to define a map, then I have to tell you, like, where do these go? Because the output's going to be R2, I need two formulas. And the formulas need to be in terms of the names I chose. So, like, I couldn't write, well, this would be the 0 map. It sends every point to 0. But if I write x2 minus x1 squared, x3 minus x1, x2, this is your observation. This is a different map than before, but it's still going to work. Then the curve equals, and I think this answers your question, the preimage of 0, which is secretly 0, comma 0.
So in that case, it is incorrect if I define it to be a map to something that is not 0.
Well, let's see. I mean, these formulas don't need to be 0. We can cook up numbers that spit out like 2, 3, for example. So does that help?
Yeah.
Yeah. So in other words, like, here's this map. Only very special x1, x2, x3 will make both of these 0. Those very special points are the preimage. In this case, a curve. Okay. Let's take a look at the questions. So that was problem 13. Problem 12 is essentially uses the skill that I assumed you had in problem 13. Okay, so when you think about problem 12, you'll realize that it's essentially, it's asking you to go from like the tangent space to the normal space, or to go from the normal space to the tangent space by using linear equations. So, yeah, let's just read this and just see if we have any questions on the statement. This is one of the new problems. Is this pretty clear? Okay. So the equation, like the answer, will be a linear equation because we have a plane. So it'll be something like 2x minus 3y plus 5z equals 7. That's, I mean, I just made that up, but something like that. Because we have a linear variety, a flat geometric object. Okay. Okay, so at this point, I'll just sort of say that I expect that all of us can get through and figure out a way to understand problems 1 through 13. And that's good because then once we're actually solid on those, we'll have sort of the basics of geometry. Which means we can start looking at, well, what if we don't want to just linearize everything and look at things that way? What if we want to deal with nonlinear equations? What if we want to deal with the actual polynomials? This will take us into the realm of ideals. Ideals is section 4. Okay? So, again, for Monday, the assignment is just make sure you're good on 1 through 13. Then, for Wednesday, we'll read section 4 on ideals, where we actually move away from linear things and we look at nonlinear equations and adding them and multiplying them together and what we can do with that. Okay. Just as an example of why this is powerful. So basically in all of like science, what you do is take the derivative, linearize, solve that. That's what you do for everything, for ODs, PDs, for literally everything, okay? But sometimes you really need to use the nonlinear equations, the actual equations. And a good example of this is, well, I don't know if it's a good example. One example in my own research is that there was a physics problem. So let me look at that. Sites. Let's see. Lie superalgebra. Well, this isn't. I need the archive version. Hold on. Okay. let me find the archive version. Archive. Do you all know the archive? Archive is where physics and math post their research. And it's free, and it's open to anybody. And so I can type Lee, Hilbert, series, Heaton. Hopefully that'll work. Okay, great. So here's the paper that myself and my friend worked on. And it's an example of where we needed to use nonlinear equations. So blah, 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 blah. Oh, okay. Here we go. So we have this object which is called, okay, wow, that formula is nice. Here we go. The chiral super Minkowski space. Something in physics that people study, and in several papers in a textbook were formulas for the coordinate algebra. But in our research, we had computed a formula that should give these same numbers, but in a different way. And so we wanted to make sure that we were correct. So we checked that our formula produced the same numbers as the one in these papers in the textbook. Nope, it didn't. It did not produce the same numbers. So, at first, we assumed we were wrong, right? But then we got more and more convinced, like, no, we did everything correctly. And so finally, we computed using Grosvenor bases, which is what we're going to learn, the symbolic computation, and we explicitly computed this list of monomials. And we counted them, and there are 46. So we corresponded with the authors of these physics papers, and we figured out that there was one little error that they had, namely, this variable should square to 0, sort of like the epsilon squared equals 0, and they forgot that part. And once this was correct, then we got the same numbers, all the formulas were good. And so you see that actually sometimes it really pays off to do explicit computations with symbolic computers in order to figure out what is going on. So we're going to be dealing with monomials a lot. Counting them is how we will determine the dimension of a variety. How we determine the dimension of the chiral super, whatever it is. I don't actually understand what it is. But that's the idea. Thanks for coming. Email me any questions.